And we are going to be starting chapter 17 on acids and bases. All right, acids and bases is just a class of reactions. What's up? Oh, shush. Yes. Good call. Cool. All right, acids and bases. This is just a class of reactions, but it's like arguably one of the most important class of reactions that there is, especially with regards to like biochemistry, because all of biology takes place in aqueous solutions, and these are reactions that are particular to aqueous solutions, okay? So it's kind of on the one hand, there's nothing too terribly special about these reactions. Hopefully you saw from the daily quiz, we're just going to be applying these concepts that we learned about equilibrium to now this new class of reactions. But they get their own little special designated chapter because they're just very important, and you see them over and over and over again, kind of all over the place, but again, especially in biochemistry. Okay? So the first thing we need to do is talk definitions here. All right, and our definition of an acid and base that we're going to use is what's called the Bronsted-Lowry definition. Okay, so let me just put down an example of an acid-base reaction, and we can try to convince ourselves that these definitions will apply. All right, so a simple example would be HCl, hydrochloric acid, reacting with ammonia to produce the ammonium ion and the chloride ion. All right, and does anybody have any wild guesses on the role that hydrochloric acid is going to play in this reaction? Acid or base? Acid, excellent. So this is our acid. The NH3 is playing the role of a base here. Okay, so the Bronsted-Lowry definition of an acid is an H+ donor and the Bronsted-Lowry definition of a base is an H+ acceptor. Okay, so what I want you to do is take a second to convince yourself that my acid, when it goes from being HCl to just Cl-, it is donating that hydrogen ion, right? It's losing that hydrogen ion in this reaction. And my base, this NH3, is gaining that hydrogen ion. It's accepting that hydrogen ion. Right? So that's what acids do. They give up their protons. Bases do the exact opposite. They accept those hydrogen ions. All right, and I kind of let it slip here, but how we would really read this H+ donor, we call those proton donors. And H+ acceptor, you would say, is a proton acceptor. All right, so let's just take a step back and see if we can't figure out why I'm calling this hydrogen ion a proton. Okay, 99.99% of hydrogen in this universe consists of one proton and one electron. Right, so if I have this neutral hydrogen atom in my hand, I'm holding one proton and one electron. If I'm going to form a positively charged ion, am I going to add an electron or remove an electron from this atom? remove an electron. So if I'm holding a proton and an electron, and all of a sudden I take away that electron, what am I left with? Just the proton, right? So a hydrogen ion is literally just a proton, a naked proton floating around. All right? So these are, hydrogen ions. They are H+, but we call them protons because that's exactly what a hydrogen ion is. It's just a proton. Okay? Now, from lab, in terms of safety, what do we know about acids and bases? Are they fun to play with and drink and everything like that? No, they're highly corrosive, right? So this sort of like terminology, proton donor, sounds like it's this like very gentle act of like, oh, sir, would you like a proton? No, no, no. Those things are shoving protons anywhere that they can put them, right? And that's why they're so dangerous, is because when you get an acid on your hand, it starts sticking protons every which place it can, and your body likes the number of protons it has, right? It doesn't want any more going on. And so that's sort of this disruptive, corrosive nature of an acid. It's not so much donating this proton as much as like forcefully giving it to various molecules, okay? All right, some more terminology here. Again, my base is accepting a proton and becoming this NH4. This is what we call the conjugate acid. All right, and my acid, when it donates that proton, it becomes the conjugate base. Okay, so your base becomes a conjugate acid, your acid becomes a conjugate base. Okay, why do we label it like that? Well, because if we were to look at the reverse reaction, my conjugate acid would be the one losing its proton, donating its proton, playing the role of an acid. And in the reverse reaction, my conjugate base would be the one accepting the proton, playing the role of the base. Okay, so that's where that terminology comes from. Look at it in equilibrium. All right, so I'm going to give another example. And I'm going to tell you that this is the acid and this is the base. And I want you to predict the products of this acid-base reaction using what we know about acids as proton donors and bases as proton acceptors. All right, so my acid is going to what? Is it going to increase in the number of hydrogens or decrease in the number of hydrogens? Decrease, right? It's donating that proton, so this becomes NO3. Okay, but importantly, that proton that it donates, that ion, has a positive charge. So that's going to leave this with a negative charge. And then my base is going to increase in number of hydrogens. All right, so we could write that like HOH, but of course, what's the normal way of writing that molecule? H2O. So then take a second and label your conjugates, your conjugate acid and your conjugate base. Right, in this case, my conjugate base is going to be that nitrate ion. And my conjugate acid is going to be water. Okay, so just using these examples, let's see if we can't figure out an easy way to determine like acid conjugate base pairs here. Okay, so we're just going to make a little table. These are acids and their conjugate bases. Let's see if we can't spy a pattern here. All right, so we said my acid was HCl. The conjugate base would be the chloride ion. And when my acid was HNO3, my conjugate base was the nitrate ion. Okay, so then given something like HBr, notice that in order to get my conjugate base, I'm going to decrease my number of hydrogens by 1. So this would just be Br. And I'm also going to decrease my charge by 1. Right, and again, that's because what's being donated is that positively charged hydrogen ion, that proton. All right, so what about HClO4? Okay, I'm going to put down a few acids, and you tell me their conjugate base pairs here. Okay.
So how do you know if it's like conjugate base or acid?
Well, so I'm telling you that they're acids, so then you're going to give me what the conjugate base is. All right, so if I want the conjugate base of perchloric acid here, HClO4, how many hydrogens should it have? None, right? Because I'm going to decrease the number of hydrogens by 1, so ClO4. And then the charge, -1. What about H2SO4? 1 hydrogen less. Decrease the charge by 1. All right? Now, this is a little weird. All of these, I mean, you may or may not sort of have seen these before, but all of these would very much so be considered acids. If you went into a chemistry stockroom, they would all be stored in like this acids container. All right? But what we need to sort of make sure that we can see in our brain is not just that we're going to talk about like molecules that are classified as acids, but molecules that play the role of an acid in a reaction. Water is not something we think about as acidic. We're not worried about getting water on our hands. What are we going to do? Rinse it off with more water? No, we're cool, right? But nonetheless, it can play the role of an acid in a reaction where it donates a proton and becomes a conjugate base. And in order to figure out the conjugate base of water, I'm just going to apply this same procedure, decrease the number of hydrogens by 1 and the charge by 1. All right, so the conjugate base of water is that hydroxide ion. Okay, and so that's what we're going to see with our acid-base reactions. It's not so much identifying molecules that are stored in that acid cabinet as much as given a chemical reaction, being able to say who's playing the role of the acid, who's playing the role of the proton donor, and who's playing the role of the proton acceptor. All right, so now we're going to do the opposite. I'm going to give you some bases, and we're going to look at their conjugate acids. And again, we got two examples that we looked at earlier. NH3, which became NH4 plus, and OH minus, which became H2O. All right, so now what's happening to the number of hydrogens? Increasing my number of hydrogens by 1. And what's happening to the charge? It's also increasing by 1. All right, so again, I'm going to put down some examples, and y'all are going to tell me what the conjugate acid of these bases are. All right, sulfate ion, SO4 2 minus. How many hydrogens am I going to add? 1. So HSO4, and my charge is going to be up by just 1, right? Minus 1. CH3O minus, again, increase the number of hydrogens by 1. You could write this like this, increase the charge. The other way, which is a little bit beyond us as to why we would do it like this, would be to write it like that. Either one of those are fine. Okay. And then lastly, again, now we see water. Water can actually play the role not only of an acid, but also of a base. So how do I get the conjugate acid of water? Same sort of procedure, right? I'm going to increase my number of hydrogens by 1, so H3O, and increase the charge by 1, plus 1. What's up?
Do we ever see that in like, I don't know, like homework or like tests or anything?
Water playing the role of an acid or a base?
Yeah.
Like all the time.
So how do we determine if it's an acid or a base?
So you'd have to look at like what the other one is, and we'll talk a little bit about that. But yeah, so for example, we'll sort of, you're sort of getting a little bit ahead, but yes, we'll be able to identify that based on some other rules, okay? All right, water, real quick, just again, terminology. We said H2O can play the role of acid or base of a proton donor or a proton acceptor. We have a special word for molecules that can do that. These are what we would call amphiprotic. Right? Meaning that they have an ability to donate protons as well as accept protons, right? Play the role of an acid or a base. Amphiprotic molecules. Yeah, so for example, this guy here actually has appeared on both of our lists, right? This can donate a proton or accept a proton. All right. Cool, so let's now go back. Let's grab this reaction here. I lied. We're going to do a different one. All right, and given this reaction, I want you to build the equilibrium expression. All right, and the other thing that we can practice is to identify the acid, the base, the conjugate acid, and the conjugate base. All right, so what's water playing in this reaction?
What's the acid? Conjugate acid.
Water's playing the role of the base in this reaction. The conjugates are always on the product side. All right, so water's playing the role of a base because it's accepting that proton, and HCl is playing the role of the acid because it is donating that proton, right? So once HCl donates that proton, it becomes the conjugate base. And when water accepts the proton, it becomes the conjugate acid. If I'm going to build my equilibrium expression here, what am I always chanting to myself when I'm building an equilibrium expression? Products over reactants. All right, so I'm going to do my product, the H3O plus, the Cl minus, over my reactants. I actually get to exclude one of these reactants from my equilibrium expression. Which one is that? H2O, because it's got that L, that liquid designation. So I just have to include that HCl. Okay? So with regard to acid-base chemistry, when you have an acid that's reacting with water specifically, this particular reaction, we would call this equilibrium constant Ka. Okay, this is what we call an acid dissociation constant. Okay, and again, that's specifically when you have an acid reacting with water. All right, your products for these reactions will always be whatever the conjugate base is of that particular acid. The conjugate base will depend on the acid itself. But since it's always water playing the role of the base, you'll always have this H3O plus as one of your products. So this guy gets a special name. This is what we call a hydronium ion. All right, and we're not going to quite get to it this class, but just to give you guys a preview, it turns out, you guys have ever heard of pH? Okay, pH is something that we're going to be studying like quantitatively here in this class. It's intimately tied to this concentration of hydronium ion. Okay, that's what pH really is telling you what the concentration of that hydronium ion is. All right, we'll get there, all right? But that's why we're going to give this thing its special name. Again, this would be an acid dissociation reaction where you have an acid reacting with water to form whatever that conjugate base is plus that hydronium ion. Okay? These Kas, acid dissociation constant, is used to measure the strength of an acid. Okay, so one of your daily quiz questions was actually this reaction in particular, and it told you that this reaction has this huge equilibrium constant, right? 10 to the 6. So is that a reaction that favors the products or the reactants? The products, right? So that huge Ka means that this reaction is pushed very favorably, very much so in favor of the products, right? So again, why does that mean that this is a strong acid? Well, because what does it mean to be an acid, right? An acid is something that donates a proton. And that's exactly what we're measuring here, this acid's ability to donate a proton, right? So the more an acid proceeds to the product side, the more it's donating that proton, the stronger the acid, okay? So again, we're going to use Ka as a way to measure the strength of an acid. A large Ka implies a stronger acid compared to a small Ka. Right? That's a weaker acid. What's up?
Is it physically represented like a small k and a little a next to each other? Like, or
A small, say it again, sorry?
are the large and small, are they physically represented like on paper with a large k?
No, it's always going to be capital K, A subscript. It's the value of that Ka that you're going to look at. All right, so we'll do an example here. So for example, I'm going to tell you acetic acid has a Ka of around 10 to the negative 5, whereas cyanic acid has a Ka of around 10 to the negative 10. And I could ask you which acid is stronger? All right, so which one is it? Let's take a vote here. Who thinks that acetic acid is the stronger acid? And what about cyanic acid? No, yeah, right? So you just compare those values of Ka. Whichever the larger value is, that's your stronger acid. That's an acid that when you place it into water will dissociate more readily, right? So indeed, acetic acid is our stronger acid. Okay? Our constants page for this particular chapter is going to be a list of all these acids with their acid dissociation constants. Okay? So we can readily compare two different acids. We'll also learn how to use those values quantitatively next class. All right? Cool. So we can use the Ka to sort of compare any two acids. There are a few acids that we classify specially as strong acids because their Ka values are just like frickin' enormous. Okay? So, strong acids. Okay, this is a special class of acids with huge Ka values. Okay, because they have such large Ka values, if we look back at this reaction here, again, we call this a dissociation reaction. Hydrochloric acid is an example of a strong acid. And so this is a reaction that we're going to assume goes all the way to completion, goes all the way to the product side here, right? There's no dynamic equilibrium going on. This thing just books it all the way to the product side. So for strong acids, we say that they dissociate completely, meaning all of that HCl is turned into, protons and chloride ions. So strong acids, we say they dissociate completely. Right, that means that the reaction goes 100% to the product side. All right, so how do we identify a strong acid? Good news, bad news. There's some memorization involved. There is 6 strong acids. We got to know those 6 strong acids. Everything else is considered a weak acid. All right, so our 6 strong acids are, first of all, most of them come from that, or half of them come from the halogen column, HCl, HBr, and HI. All right, there's one halogen that's left off this list. HF is actually not a strong acid. It is a weak acid. All right, and then the other ones have these polyatomic ions on them. HNO3, HClO4, and sulfuric acid H2SO4. These are our 6 strong acids. All other acids are considered weak acids. Okay, and so what do we mean by weak acids? Just in contrast to our strong acids, importantly, these do not completely dissociate. All right, so an appreciable amount of reactant remains at equilibrium. Okay, so while it might be a pain in the butt to have to remember these 6 strong acids, what we're going to see is that from a quantitative standpoint, the strong acids are actually the easiest to work with, right? Because all we got to do is assume that 100% of what we start with is going to be dissociated, is going to react. The weak acids are going to be much more of a pain in the butt. We're going to have to actually consider that equilibrium expression, consider their equilibrium values when we're figuring out how much dissociation happens, because they don't fully dissociate. We still got an appreciable amount of reactant that's left over at equilibrium. Okay, so the strong acids are actually the easier of the 2 to work with. So what do I mean? So let's see. Again, we're going to stick with this same reaction. let's say R. All right, so let's say that I take 4.5 moles of hydrochloric acid and combine them with water such that the total solution volume is half a liter. What is the concentration of hydronium ions? When we put it in brackets, we want the concentration in molarity. Okay, so when I say what is bracket H3O plus, I'm asking what's the concentration of hydronium ions in molarity. All right, again, molarity is going to be the like concentration of choice here. We do talk in molality every once in a while. We saw that those colligative properties, some of them are proportional to concentrations in molality. But for the most part, we're going to stick with molarity in the course. Okay. So first of all, let's just remember, what is the definition of molarity? Big M. Moles of H3O plus over liters, what? Solvent or solution? Solution. All right, so this problem is actually deceptively easy here as long as we can identify that HCl is a strong acid. Okay, if I'm going to do my concentration of H3O plus, do I have my liters of solution from the problem? Right, it told me that the total volume once I mixed everything together was that 0.5 liters. Okay. But then how do I get the moles of my hydronium ion? Well, remember what it means to be a strong acid. A strong acid just means that 100% of that HCl molecule, 100% of those HCl molecules are going to be converted into hydronium molecules, right? So if I start out with 4.5 liters, move this up here. Not liters, sorry, 4.5 moles of HCl, how many moles of hydronium ions am I going to get at the end? 4.5, because 100% of those HCl molecules are converted into hydronium molecules, right? Hydronium ions. Right, so again, the problem is deceptively easy as long as you can make sure to identify that you're talking about a strong acid. Right? So then for my concentration, that would be the 4.5 moles of H3O plus. Take this down here, I guess. Punch that into my calculator. Should get 9. How many sig figs should I have? Right, again, I won't sort of like brutalize you with sig figs for our ICE tables, and when it gets too complicated, for a simple division problem, we better be able to do sig figs, all right? So not just 9, but 9.0 molar H3O plus. All right, so again, strong acids, it's this special class of acids. Only these 6 apply, but they fully dissociate, right? So we can assume that 100% of that strong acid molecule reacts and forms the product, our hydronium ions. What we'll pick up with next time is weak acids. And what we're going to see is because they do not completely dissociate, we're going to have to use that equilibrium expression to figure out how much product we get. Because what acid are we talking about? HCl. Is HCl on our